Okay, 2.2 is on the chain rule. And the idea here is about sort of the composition of functions. What happens if I have a function within a function and I need to differentiate it? So let's just think back to looking at composition of functions without the differentiation part. So looking at this review example, f of x equals 3x squared, g of x equals sine of x. The first thing we're being asked to do is find f of g of x. And what that means is I'm substituting what g of x is into the function of f of x. So f of g of x means that I'm plugging g of x in anywhere that there was an x in the original function. And that squared sign, this could be rewritten as 3 sine squared x. That's also completely accurate. Now if we look at g of f of x, we're now going to substitute f of x into g of x. So g of x is sine of x, except not sine of x anymore because we're going to substitute f of x in sine of 3x squared. So really remembering how composition of functions work. There's two functions existing that are being manipulated according to the other function. And this is where the idea of the chain rule comes in. The chain rule's job is to differentiate compound functions, a function within a function. Notice that one function will be inside another function. And so what that looks like is when you're taking the derivative of a composition of functions, you're going to use the chain rule. We're going to prove this in class, but right now we're just going to practice how to use it. So what you're going to do is you're going to take the derivative of the inside function, and you're going to multiply that by the derivative of the outside function, evaluated at the inside function. Notice this is not the product rule. There's no addition. This is all still being multiplied, but you're going to take the derivative of the inside function and multiply that by the derivative of the outside function. So let's look at some examples. I think that's going to make this make a lot more sense. So this example up top says f of x equals 5x plus 1 quantity squared. So there's two functions happening. There's a function that is basically just x squared. That's the outside function. Then there's a function that is 5x plus 1. That's the inside function. So inside function, outside function. So the derivative of the inside function, is just 5. The derivative of 5x plus 1 is 5. The derivative of the outside function, x squared, is going to be 2 times what's already in there. So we're not manipulating what's inside the function at this point to the first power, right? If I square something, I drop the 2 and reduce the power. So this is really going to be, let's multiply all of this out, 50x plus 10. So you're taking the derivative of the inside, which is 5. You're taking the derivative of the outside, which is 2 times the quantity 5x plus 1 to the first power, and then you're simplifying. And that's really all that we're covering in this section. So let's just work through some more example problems. Feel free to pause the video, work through these on your own, and then come back and check and see how you did. So on number 1, the inside function is x squared plus 5. The derivative of that is going to be 2x. The outside function is x squared plus, is to the third power. So we're going to drop the 3 down, keep the inside function the same, and reduce that exponent. So we could simplify this. This is really just 6x times x squared plus 5 quantity squared. Number 2, the outside function here is the squared sign. I know this one is a little harder to tell. The inside function here is cosine. I'm going to say that again. The outside function is the squared portion. The inside function is cosine. So if we're taking the derivative, which you could write as y prime or dy dx, the derivative of the inside function is going to be negative sine of x. The derivative of the outside function, the derivative of squared, basically, is 2 times cosine of x to the first power. And then I'm just going to write this a little bit nicer, negative 2 sine x cosine x. Okay, number 3, the outside function is the cubed. The inside function, and actually this has a double chain rule. You're going to do the chain rule twice. So let's see if I can squeeze this in. The outside function is to the third power, and then we have basically what we just did on number 2 inside the function as well. So we're going to perform the chain rule twice. So f prime of x is, the inside function is the stuff that we just found. So I'm going to take this answer that we found on number 2, and I'm going to use that for cosine squared. So the derivative of the inside function is -2 sine of x cosine of x. And I'm running out of space, so I'm going to move this here. Now we're going to multiply that by the derivative of the outside, which is 3 times cosine squared x plus 5 squared. So let's see if I can write, I'm going to use the space down here, fit this all on here. So the derivative is going to be, and since this is all being multiplied, -6 times sine x cosine x times cosine squared x plus 5 quantities squared. And there we go. So it is possible that we have to do the chain rule twice, just like it's possible that we might have to do the product rule twice. So let's go ahead and move on to the next examples. Number 4, the outside function is tangent. The inside function is 5x. So the derivative, y prime, is going to be secant squared. I did it backwards, that's okay. Secant squared of 5x times the derivative of the inside, which is just going to be 5. Let's rewrite that. Y prime equals 5 secant squared 5x. For number 5, I'm going to start by rewriting this with a fractional exponent, which I just think makes life a little bit easier. So the inside function is x squared plus 1. The outside function is something to the power of 1/3. So f prime of x, the derivative of the inside is 2x. The derivative of the outside is x squared plus 1 to the negative 2/3 times 1/3. I'm just going to stick that in front. And you are more than welcome to leave it just like this. You could also write the whole thing as a larger fraction. If you really wanted to, you could move this to the denominator to have a positive exponent, but I don't think that there's a point in you doing that. Okay, number 6, I'm going to start by rewriting as well. So now the derivative of the inside is going to be 2x minus 5, the derivative of that is 2, times the 5 that was already there, times, I'm going to drop my exponent down, -2 times 2x minus 5 to the negative 3rd power. So y prime, equals, what is that, -20 times 2x minus 5 to the negative 3rd power. Number 7, simplify by factoring the least power. And what I mean by that is after you find the derivative, because that's the direction for all the problems in here, after you find the derivative, you're going to factor out using the least power to simplify as much as possible. So I'm going to rewrite this problem first. Then I'm going to find y prime. Y prime, here we're going to use the product rule and the chain rule. So I'm going to deal with both of those things. So the derivative of the first function is 2x times the second function unchanged, that's how the product rule works, plus keep x squared the same, and now we're going to have to deal with the chain rule with this second function, 1 minus x squared to the 1/2 power. So I'm going to drop the 1/2, 1 minus x squared to the negative 1/2 times the derivative of the inside, which is 2x. Now I'm going to do some simplifying. So 2x times 1 minus x squared to the 1/2 power, plus these 2's are going to divide out. This is going to become x to the 3rd times 1 minus x squared to the power of negative 1/2. In terms of derivatives now, we're done. However, the directions say simplify by factoring the least power. So I'm going to factor out 1 minus x squared to the negative 1/2 power. That's going to bring me here, and you can check if we distributed, we would get back to exactly where we were the step before. Now I'm going to simplify inside parentheses. or inside the red brackets. I'm going to distribute 2x, and then I'm going to combine like terms. That's going to bring me here, and I guess if I could do one more step of factoring, I could actually take an x out, which would give me the following. I think either of these last two steps would be an acceptable version of the answer based on these directions. But notice that was a great example. It uses the product rule and the chain rule both in the same question. All right, very last question. If P of 2 equals 5, Q of 2 equals 3, Q prime of 2 is 2, P prime of 3 is 4, and Q prime of 3 is 2/3. That's a lot of information. Find the derivative of P of Q of x when x is equal to 2. So the very first thing I want to do is I just want to write out what this is talking about. So it's asking me for d dx of P of Q of x. Let's write out what that means. So what that means is I'm going to have P prime of Q of x times Q prime of x. The derivative of the inside multiplied by the derivative of the outside evaluated at the inside. I actually kind of flipped the order of that, but that's okay. So if I'm doing this for x equal to 2, that's going to give me P prime of Q of 2 times Q prime of 2. Well, Q of 2, according to this part up top, Q of 2 is 3. So I'm going to end up taking P prime of 3. And Q prime of 2 is 2. So P prime of 3 times 2, P prime of 3 is 4, 4 times 2 is 8. So I would want to see probably these first two steps, or at least the second step, and then I think going straight from there to the answer would probably be fine. So make sure you understand how to use the chain rule, that you challenge yourself on some problems where you're using the chain rule more than once, or where you're using the chain rule and also using the product rule or the quotient rule. Go back and work through these problems again, and then make sure to check out the extra practice for 2.1 and 2.2 if you feel like you need some more support. Thanks for listening.